All right, we're now recording. So in terms of this picture, if I draw here in red the derivatives, the chain rule says the derivative of a composition is the product of the derivatives. Okay, so in a way, the chain rule is kind of easy to remember. I want to help you make it easy to remember. But in practice, you have to keep track of a couple things. So let me just throw some details in here. And what we're going to do today is we're going to spend some time practicing the chain rule. And then I'm going to talk about the derivatives of some other elementary functions. And then we'll do more practice with the chain rule and the other rules. So the details are, if we've got an independent variable, ooh, I should want that to be, oh, of course, I did this notation wrong. What did I do wrong? Can anybody see how I totally messed up my notation? What I did here is very inconsistent. Can somebody see one inconsistency in what I've done up here?
You went to G from F and then went to,
Yeah, exactly. I
or went from F to G
yeah,
and
yeah,
then G to F. Yeah.
yeah. So that is wrong and that is wrong, right? So I need to change those. So this should be the G and this should be the F. This stuff is right. This is okay. But I need to change these. Okay, so that's not so bad. Everything else I did is right. Except down here, I want to put a G. And then, so G takes X to a Y, and then F takes that Y to a Z. So then we say the derivative with respect to X of F composed with G of X is F prime of G of X times G prime of X. Okay. So that's one way we can write the chain rule. Another way we can write it is we can say the derivative, the chain rule of the composition is df dy times dg dx. And another way we can write the chain rule is dz dy times dy dx. And that's kind of neat because this other derivative here, if the far left-hand side, f composed with g takes x to z. And so a person could write the left-hand derivative, the derivative of the composition, as what's dz dx? And the chain rule tells you it's dz dy times dy dx. And there's a cool little pattern here where it suggests there's cancellation. Okay, so that cool pattern kind of was one of the things that makes Leibniz notation interesting and valuable, and sometimes fruitful. But for us in this course, while you're learning this, I suggest you just focus on that formula. You focus on learning how to use that formula. And that as you become comfortable with the computations using that formula, then you can start thinking of these other ways of writing down the derivative. Okay, so let's do some examples. So the way I want to do this is I am going to write down an example, and then I'm going to ask you to use the chain rule to calculate it, to work it out on some scratch paper in front of you. And then maybe I'll ask anybody if they want to share what their calculation was, and they can share it either verbally or they can type it into the chat. And then I'll do the computation for everybody. Okay. So first example. Consider the function f of x that's 3x squared. You don't need to use the chain rule to calculate the derivative of this, but you can, and I want you to use the chain rule. Okay, so what's the derivative of the quantity 3x squared according to the chain rule? I'm going to set my timer for 1 minute. Ask people if they have any guesses, any educated guesses. So go for it.
Do we just type it in, or are you going to do like a 3, 2, 1 thing, or?
Yeah, I'll ask you in a minute if you want to share it, and you can either type it in or you can say it verbally.
Okay.
Okay, 10 seconds. We could. All right, so time's up. So using let's use Zoom's functionality here, and you can either do it in the participant list if I can find it. Okay, so there's a participant list I can look at. You can do it. You can either say yes in the chat, or raise your hand in the participant list, or raise your hand in the gallery, right? Using your reaction at the bottom of the Zoom window. So anybody want to share what they got?
Sure. 6x.
Oh, okay.
Oh, sorry.
It's okay. It's all right. All right. So Jet says 6x. So let's put that in the answer book. And everybody agree with this? Thumbs up if you agree. Dunya agrees. Evan agrees. Luke agrees. Summer, Andre, Athalia, Robert. You are so agreeable, but it's not right. Anybody want to suggest something else? I think it's 18x. Anybody else get 18x? Brandon, you got 18x? I'm trying to.
I just found out why it is 18x.
You just found out why it's 18x?
Yeah, I got 6x and I looked at it again. I realized why it's 18x.
Yeah.
Do you want me to explain it? See if I got it right.
Sure. Go ahead.
So since it's 3x to the power 2, you do 3x times 3x, which would get you 9x squared. And then when you do power rule, then you get 18x.
Yeah, right. That's exactly right. That's an exactly correct way to look at it. All right. But you didn't use the chain rule. So you use the product rule, or you use some algebra first and then differentiated using the power rule. So you got the right answer. But what I want people to see is how to use the chain rule on this.
Okay.
So anybody want to?
Oh,
Do you see how you can use the chain rule on this, Robert?
I could do it.
Sure.
So I split up the 3x squared into like two separate equations. So my g of x would be 3x, and then my f of y would be y squared. So I first differentiated the y squared, and that got me 2y to the power of 2 minus 1, which just gives me 2y. And then I differentiated the 3x, and that got me 3.
Okay.
So I remade the equation, and I got 2 times 3x times 3, and that got me 18x.
Yeah. Yeah, I like that. That's good. All right. Thanks, Robert. So I wrote down as Robert was talking what I heard him do. Okay. He identified these two functions, and what he was saying is that 3x squared can be viewed as the composition of these two functions. So it's going to be like this. So first, the function g multiplies the input by 3, and then the function f squares everything. So first you get 3x, and then you square everything. And then the derivative of the composition by the chain rule over here, it's the derivative of the first function, the f, and I'm just going to write the derivative of g. And so what Robert did, he calculated those derivatives. And so he said the derivative of my f is 2y, and the derivative of my g is 3. But y is 3x. Oops. And so he got this down there. And that's 18x. All right. So to repeat that and say it in a slightly different way, here, if you think of composition in terms of inside functions and outside functions, outside being the last thing, the last rule you apply. In this case, the last rule you apply before you get your final output is squaring. The first rule you apply to your independent variable here is multiplying by 3. So the chain rule says you take the derivative of the outside and you multiply it by the derivative of the inside. So in this case, the derivative of the squaring function, you just use the power rule. Okay, and you leave the inside alone initially. But then the chain rule says, oh, you got to remember, in the end, you have to multiply by the derivative of the inside. And that's how you get the derivative. And then simplifying, we get 6 times 3x to the 1 is 18x. Okay, should we do another one? let's differentiate this. Let's differentiate 4 minus 3x to the 5th power. Okay, try that. I'm going to set my timer for a minute, and then I'll ask if people have solutions. So go ahead, chew on it. Ten seconds. All right. So by either saying yes in the chat or raising your hand in the participant list or doing a thumbs up or something like that in your reactions in the gallery, who thinks they got an answer they've got some confidence in that they want to share? Okay, Brandon's got thumbs up. Brandon, the only person? How many, Robert, Luke, good. How many people have an answer that they don't have any confidence in? And how many people don't have an answer? Okay, so Luke, why don't you want to either give us your answer and you can type it in the chat, or you can vocalize it, and I'll try to capture it in my notes. But why don't you give it a shot? You gave your thumbs up.
The answer I got was 15 times 4 minus 3x to the 4th.
Okay. All right. So how many people agree with this? This looks good to them. Evan's thumbs up. Anybody else? How many people, anybody have another answer that they want to share? So Brendan, you said you had a calculation and somebody else said they had one. Robert, you said you had another calculation. Brandon, you want to share yours? Brandon's throwing it into the chat. Okay, and Jet, put this.
I forgot the raise to the 4th.
Okay, so you want the 4th there, and
Yeah.
And Brandon, you're doing that. Dunya, you got that. What did you do, Brandon? 4 minus 3x? Oh, I see. Okay, so this is great. So I see a pattern in all these answers. So I'm looking at all these answers, and absolutely right. That should be to the 4th power. You know, you should think of this here as like a polynomial in the 5th degree. And we know when you take a derivative of a polynomial of degree 5, you're going to get a polynomial of degree 4. What, you know, the differentiation decreases your degree. So this is exactly right. And you were using the power rule to do this clearly. Every one of these solutions here has left this thing alone. And that's good too, because if you look at my solution up here, when I was calculating this derivative, I left that thing inside, what I call the inside function alone. So all of these things have a 15 here. So the number out front is not 12. It looks like, 12 is a product of 4 and minus 3. But really what's happening here is when you take the power rule, that 5 comes down as a coefficient. So when we take the derivative of this baby, the first thing we do is that we just look at that outside function and we take that derivative. So the exponent becomes a coefficient. The new exponent is 1 less than the previous. And because there's something complicated in here, I know I've got to leave room for the chain rule. And so the chain rule says, what's the derivative of this? So the derivative of this, well, I'll look at it term by term. The derivative of 4 is nada, right? And the derivative of negative 3x is negative 3. So that's where we get this negative 15. Okay, so that's the answer. All right. Good, Dunya?
Yes.
Okay, good. Everybody good with this? Follow the work? Should we do another one? So let's differentiate. Differentiate that. Give you a minute. All right, time's up. So signal to me either in the chat or in some other method if you have an answer you've got some confidence in. Okay, Jet's got her hand up. Alexia's got her thumbs up. Okay, we got some confidence here. So how about Athalia? I haven't heard from you in a little while. Why don't you want to tell us what your answer is? You can either vocalize it or you can throw it into the chat. Whatever you want.
I feel like I should have waited for you to say who's not confident in their answer.
Oh, you want me to do that? Okay, let's do that. Let's do that.
That's okay. I don't mind sharing.
No. Let's do it. Okay.
Okay.
Is there anybody here who's has an answer but isn't confident in it? And remember, that's fine. We're learning this stuff. Don't be bashful about it. Anybody not have an answer? Okay, Athalia, I tried. What do you think? You're on mute.
I got 21 parentheses 7x plus 1 at the end of the parentheses to the second power.
All right. Did anybody else get anything? Or anybody else get this one? Was this anybody else get the same derivative?
I did.
Levia, Jen, Brandon, Andre, Alexia. Yep. Well, that's good because that's right. That's exactly right. Want to do another one? Want me to Same level, raise the level a little bit.
Same level.
We'll do one more same level, and then I'll raise the level of difficulty just a little bit.
Just raise it up like people want to raise it. Go ahead.
No, that's all right. Let's do. Okay, so take 30 seconds to try this one. Okay. Anybody have an answer they want to share? They confident enough to share? Anybody else? Alexia? Good. How about you, Ali? No? Summer? No? All right. So somebody give me a guess. What's an answer? Somebody who was pretty confident they got an answer. What do you get? Alexia, you said you had something, right?
Yeah, I'm typing it
Okay.
right now.
All right. So Alexia said she calculated this 160 plus times quantity 4 plus 8x all to the 19th power. Robert and Evan typed in exactly the same thing. Jet, same thing. Now, math isn't a democracy, so just because everybody's getting the same answer doesn't mean it's right. But it turns out that that's exactly right. That's exactly right.
Okay, good. The way you were saying it, I thought it was wrong.
Yeah. So just let me put the steps in here because I didn't put the steps in for the third example. When I differentiate, so I see this in my mind. I see, well, here's my inside function and here's my outside function. So let me use the power rule first, and I'll leave the inside thing alone. And then I know I need to multiply by something, and that something by the chain rule is the derivative of the inside. And I can see the derivative of 4 is 0, and the derivative of 8x is 8. So the derivative of my inside function here is just 8. So I get that. And then simplifying, I move all the constants together and multiply them, and I get 160 times this. All right, hey Lupe, do you want me to put you on the spot? Do you want to perform?
Sure.
Okay.
I can do one. I'll step it up.
Do people want to see Lupe do an example in front of everybody? Put him on the spot. Oh, look at this! They want to see blood, Lupe. They want to see you perform. Okay.
Okay.
All right. So here, let me. Do you want to share your tablet? Do you have your tablet with you?
No, I don't have it with me. Is it okay if I just verbalize it and you write it?
Sure.
Okay.
Okay. So let me write down the problem first. So how about I'm gonna jack it up a notch. So I'll have you do one of these first, and then I'll have everybody else do something like it. So let's say I've got the polynomial x squared plus 3x plus 10, and I want to raise that to the 20th power. What You want to tell people what you do to calculate the derivative?
Oh, yeah. Okay, so what we do is we look at this as a whole, correct? And we apply the power rule. So when we apply the power rule, we go ahead and put the 20 as a coefficient, and we lower the exponent by 1. And we, yes, and we rewrite the whole expression in the middle. The x squared plus 3x plus 10. And then what we do, we multiply it by the derivative of the inside, which we can see that from x squared, we get 2x. And then from the 3x, we get just 3. So times 3 as well. Oh, wait, never mind, I'm sorry. That is a plus 3.
Ah,
2x
okay.
plus 3.
Good.
Sorry about that. And then because of the 10, we get a 0. So just we could leave it like that. And then what we can do is go ahead and combine the 20 with the 2x plus 3. Wait, yeah, we could do that. We could factor the 20. We could go ahead and get 40x plus 60 times the quantity of x squared plus 3x plus 10 to the raised to the 19th.
Yeah, good. Okay, everybody good with that? Everybody agree with what Lupe did? Yeah, he basically did what we've been doing with the simpler examples. Okay, so why don't we all try this with why don't you try to differentiate this? 10x minus 2x cubed to the 4th power. Take a minute to see what you get. And I'll shut my windows so I don't hear the lawnmowers. $15 more seconds. All right. Time's up. How many people have an answer that they kind of like? All right, good. So 6 or 7 people. Okay, who wants to share one? Anybody want to share one? Andre, you had your said you liked one, I think, didn't you? Oh, and Ali too. Yeah. Why don't Andre and Ali? Why don't you either throw yours into the chat, or Andre's going to type it. Ali, you can type or vocalize it. All right, so Andre typed this: 40x minus 24 x squared parentheses 10x minus 2x cubed parentheses cubed. All right. Ali, is that what you got?
Yes, but I got 8x, not 24x. But I think that might have been just a multiplication problem.
8x, not
Yeah, I got
24x, like here.
yes.
So did you get 8x squared or 8x?
I got 8x.
So you got like 40x minus 8x times this stuff.
Yes.
Okay. All right. Anybody have any other answers? So Summer says, I got that, but without the squared after the 24x. So Summer, you say that you got 40x minus 24x times 10x minus.
Oh, I think I already know what I did.
Okay.
Yes, that's what I got.
Okay. So that's what you got. So
Yeah.
Ali's retracting his work. So Ali, what do you think you got instead? Let me undo that.
So what I did wrong was I did the 4 times 2x to the 3 power, and then that would have been 8x. And I just didn't write the third power timesing the 8 times 3, which would make it 24. I just didn't write it down.
I see. So you think that should be a 24.
Yes.
So you agree with Summer.
Yes.
Okay. Okay. So anybody else want to share something they got? No?
Brandon put his on the chat.
Oh, okay, Brandon. Oh,
Or
yours
just
is
I don't-
yours is a little different. So 40 minus 24x squared, 10x minus 2x cubed to the third power. Okay, so we've got 3 different solutions here. So let me tell you what I see. I love the 3s, right? There was a 4 there. Doing the power rule, I love the 3s. Right. Also, this thing that we're taking to the 4th power of, right? I should see that in our pattern as well, and it should be raised to the 3rd power. So all these 3 different solutions have that in common. That's great. Big thumbs up. In these first 3, what I want to see, or actually there's only 2 here. I want to see parentheses here. Don't forget those parentheses. Okay, because Brandon got them, right? He got those parentheses, and that's great. So don't forget those parentheses, because right now, with the order of operations, this solution, for example, it's 40x minus the quantity where you're multiplying those 2 things together. But really, you want to multiply this whole thing times that whole thing. Okay, people see that? I'll work through the solution this so you can see where that comes from too. Okay. Okay. So yeah, which one of these is right? That's a good question. I think, yeah, the first, if you put the parentheses here on the first one, I think the first one and the third one are right. I think you're going to be looking for the derivative of this, right, from the chain rule. And the derivative of this is going to be 10 minus 6x squared. So I'd be looking for an x squared here on these terms. Because without the x squared here, you could simplify this down to 16x.
Oh, okay. Yeah, that makes sense.
Okay, make sense? Okay, so let me show you how I would do this, right? So when I apply the chain rule, I take that 4 down, and I reduce the exponent by 1, and I get that. And I'm going to put this here because I know I'm going to have to put a derivative in there because of the chain rule, because this is a complicated thing. One function composed with another function. So now here I need to put the derivative of the inside. So I can do this term by term. The derivative of 10x, I know that's 10. And then I'll do a minus the derivative of this thing, 2x cubed, and that's 6x squared. Now here I will tell you, you could leave it like this. this is a perfectly good way to leave it. You know, you could multiply, you could multiply this 4 through all this stuff if you wanted. But the way this is written right now is it's kind of in factored form in a way. It's close to a factored form. But if you wanted to multiply it out a little bit more, you could multiply the 4 through the other thing and get this. Okay, and that's perfectly legit. All right, let's do one more example and we'll take a break. Okay. So how about okay, let's differentiate that. I'll give you a minute. Then don't overthink it. Just think about it the right amount. Okay, minute's up. How many people got an answer that they kind of like? How many people got an answer that they want to like? How many people were confused by the -2? Anybody? So Alexia has a thumbs up on that, but I bet you other people were too. Anybody have a solution that they want to share with the group? You can throw it into chat or vocalize it.
I have a solution, but I really don't think it's right.
Okay, that's fine. What is it?
Negative 6x and then parentheses x squared plus x plus 1 parentheses and then to the negative third power.
Okay. Anybody else have an answer that they want to share?
I do, but I made it into a rational function if that's fine.
That's fine.
Okay, so I got negative 4x minus 2 all over x squared plus x plus 1 to the third power.
Okay. And Luke he wrote negative 4x minus 2 in the chat. He's writing us x squared plus x plus 1 to the negative third power. Anybody else have an answer or a proposed answer? Okay, so I'm not hearing anything. Let me just make some commentary. These two are the same. Okay, take a look and review this and notice that those two are the same. Okay, and I think they're both correct. We'll work through it and and C. So Alexia, I like yours. You got that -3. I absolutely positively expect that -3 to be up there. But the 6 here makes me look around for a 3. And I think that you pulled down a -3 instead of a -2. So I think there's a little error there. So that's not exactly correct. Let's look at what Z prime will be here. So if I'm going to take the derivative of this thing, I'm going to use a chain rule, and I'm going to starting with the power rule, and I'm going to look at this, and I'm not going to be intimidated. I'm not going to overthink it. I'm just going to use the power rule the way I'm used to using it. Take that exponent down, and the new exponent is 1 less. Okay, and the chain rule tells me I need to multiply by something, and the something I need to multiply is the derivative of this inside. And so that's the derivative of 2x, or derivative of x squared, which is 2x, plus the derivative of x, which is 1, plus the derivative of 1, which is 0. Doesn't matter. So if I move these things around a little bit, I get this, which you can see is the same as both of those there. If you multiply this -2, you distribute it through there, you get -4x minus 2. So that's good. All right, and that's how you take the derivative using the quotient rule or the chain rule of this thing. Okay, so hopefully that practice was helpful for you, and it will help you find more success as you try to practice the chain rule and other differentiation rules on your own. Let's take a 5-minute break here, and then we'll come back and I'll turn our attention to some other elementary functions and look at their derivative, and then we'll have more examples that we can use to play with the chain rule. All right, so I'm going to set my timer for 5 minutes, and we will all meet back here in 5 at 9 o'clock. Hi, Peter. How are you? No, we're not going upstairs. Thanks, Lupe. So now let's look at these limits. So I'm going to claim that the limit as h goes to 0 of sine of h over h equals 1. So how could we prove that? Or well, not how could we prove that? How could we convince ourselves that that's true? Well, one way we could convince ourselves is by gathering evidence, as if we were scientists. We're not scientists, we're mathematicians, but a scientist might gather evidence. And we might make a table of values, right, to gather numerical evidence that this trend happens. And we've done that before in this class. Or we might take a look at a graph of sine of x over x and look to see what it's doing near x equals 0, right? Because after all, that's what a limit is. You're looking at a function near, in this case, h equals 0. So if we made a table of values and if we graphed, we'd say, yeah, there's evidence that this limit equals 1. And I'll let you do that on your own time. Mathematicians want proof. And so your textbook has a proof of this limit. And the way the proof works is that you use some trig. And by that, I mean knowledge about triangles, to show that cosine of h is less than sine of h over h is less than 1. When h is near 0. And then if you take the limit of everything, take the limit as h goes to 0 of all of it, then the squeeze theorem proves your result. Because as you take the limit of everything here as h goes to 0, well, as h goes to 0, 1 goes to 1. As h goes to 0, cosine, which is continuous, goes to cosine of 0, which is 1. So that means that this thing must also go to 1. So that's why this is true. So that's cool. So let's look at the other mystery limit. So I claim that that limit is 0. So you could gather evidence in a similar way, right? You could make a table of values of this thing for h is close to 0. You could look at the graph of this and inspect the graph near h equals 0. And all that would support this idea. But we're mathematicians. We want proof. And it turns out the proof here isn't too hard. So I'm going to show it to you. The other proof isn't that hard either, but it's a little complex. So what I'm going to do here is I'm going to multiply the top and the bottom by the same thing. I'm going to multiply the top and the bottom by cosine of h plus 1. And when you multiply something in the numerator and the denominator by the same thing, right? They cancel out, so it's like you're not doing anything. A favorite trick in mathematics. Now simplifying upstairs, I get cosine squared of h minus 1. And then downstairs, it's the same sort of thing. But there's a trig identity that says sine squared of h plus cosine squared of h equals 1. And if you subtract cosine squared of h from both sides, you get sine squared h equals 1 minus cosine squared h. And look what's up in the numerator. In the numerator, it's almost this. It's the opposite of this. It's minus 1 times this. So I can rewrite my numerator as minus sine squared h. And so here's where the cool thing happens. So rewriting what I'm taking the limit of as this product, I can then use the limit laws to say the limit of a product is the product of the limits. And as h goes to 0, cosine of h goes to 1, so my denominator is going to 2, but my numerator, it's going to 0. So this whole second term is going to 0. Meanwhile, I just proved that this limit goes to 1. So 1 times 0 is 0. And that's what I wanted to prove. That's exactly what I hope to prove. Any questions about this? All right, and so here's why I'm showing this to you. So let's go back here. So I did all these calculations. We're trying to figure out what the derivative of the cosine is and the derivative of the sine is. And here are those pesky limits. Well, I just proved, what color should, I'll do this in green. I just proved that this limit is 1 and that this limit is 0. So that tells me that the derivative of the cosine is minus sine, right? Because that's all that's left here. After this goes to 0 and that goes to 1, is this minus sine, because that gets annihilated by that 0. So that's really cool. Let's look down here. The derivative of sine. Well, we know that the sine, this limit goes to 1, and this limit goes to 0. So what am I left with? I'm just left with this cosine. So the derivative of sine is cosine. So this is cool. So I'm going to move forward and write this conclusion down. Thus, the derivative of sine is cosine, and the derivative of cosine is minus sine. Yeah, so these are formulas you need to memorize. You don't need to memorize the proof that I showed you. The only thing that's kind of cool that might be worth remembering is this limit statement and this limit statement. But beyond that, don't worry about the proofs. Also remember that these formulas are not obvious. It's not obvious that this is true. Now, I would strongly recommend that you go to like Wolfram Alpha and plot these together and see that it works. Look and see that, yeah, indeed, the cosine, has all the signature elements of being the derivative of the sine, right? When this is a function that gives you the slopes of the tangent lines to the other function. So go do that. That's a good exercise for you to do. So I'll do this too. So if I were to put in the tangent and I ask what's the derivative of the tangent? Well, it's secant squared. What's the derivative of the cotangent? It's minus cosecant squared. What's the derivative of the secant? It's secant tangent. And what's the derivative of the cosecant? It's minus cosecant cotangent. Okay. So you should know these. You should memorize these. You should have these close at hand mentally. Okay. But I'm going to tell you, prove these. Derive these is the way we like to think of them. Derive these from rules of differentiation. Okay. If you can derive these formulas using the rules of differentiation, you'll never have to memorize them. Okay. And that's always better. If there's a way you can remember a formula just by remembering something similar or simpler, and a way to get the more complicated thing, that's always better than memorizing something. Okay, because if you know how to derive a formula, then you know why the formula works, and that's super good. Okay, so I'm not going to do this right now, but things you can do to, now that you know what the derivative of sine and cosine are, is you could say, hey, what's the derivative of sine x squared? Or even, what's the derivative of sine squared x? What's the derivative of tangent of 2x plus 1? You can start calculating these types of compositions of functions, or their derivatives. Okay? And we'll, if we've got some time at the end of class, we'll do that. But I want to encourage you, I just want to say that you're at a place where you can do that now. But I want to talk about exponentials. So if we've got a function of the form b to the x here, where b is a positive number, that's what's called an exponential function. The variable is in the exponent. And let's find a formula for the derivative of an exponential. So the first thing I want to point out is that if you play a game where you say, well, I'm going to draw an exponential function. So suppose this is y equals b to the x, and you say, I want to draw the derivative of the exponential function, you're going to end up drawing something that looks very similar. And as you look at that, you can ask yourself, well, what kind of elementary function is that? Looking at that red curve, what kind of elementary functions have that shape? And there aren't many. I'm going to let you think through it, but there aren't many. Okay? That's not a polynomial. It's not a logarithm. It's not a root function. There aren't many functions that have that shape. And in fact, you wouldn't be surprised to know that it's exponential functions that have that shape. So sketching the graph suggests that the derivative of an exponential is going to be an exponential. And then the trick is finding a formula for that exponential. So let's start that process. So let's let f of x be b to the x. And what's f prime of x? Well, that's the limit as h goes to 0 of b to the x plus h minus b to the x all over h. And by the law of exponents, I'll do this in a different color. Let me do it in the gray. B to the x plus h is the same as b to the x times b to the h. So in my numerator, I can see that I've got a common factor of b to the x. I can pull that out. So this is the same thing as the limit as h goes to 0 of b to the x times b to the h minus 1 all over h. And oh my God, watch, look at this. Look at this. This thing here doesn't depend upon h at all. So it's constant with respect to h. So that means I can use the constant multiple rule for limits and pull it out to the front. And I'm left with this. So the derivative of an exponential, just for emphasis, let me write this here. The derivative of b to the x is b to the x times something. And this is going to be a number. Okay. And it looks like it's a number that depends upon b. So I'm going to rewrite this on the next page. Looks like the derivative of b to the x is some constant I'll call b that looks like, or c, that looks like it depends upon b times b to the x. Okay. And here, this constant is the limit as h goes to 0 of b to the h minus 1 over h. So let's look at and see if we can figure out what this function might look like. Okay, how does this coefficient change as b changes? So what I can do is I can do this. So let's consider b equals 2. And so I'm going to make a table. So I'm going to have a row where I have h values, and then I'm going to have rows of the values for this. So it's going to be 1 over h times 2 to the h minus 1. So if I choose h equals 1 and 0.1 and 0.01 and negative 1 and negative 0.1 and negative 0.01, you throw these into a machine and you get the number 1, 0.7177, 0.6956. And then at negative 1, you get the number 1/2, and then you get 0.6697, 0.6908. So it looks like as your h's are getting closer to 0, these numbers look like they're getting closer and closer to some number. So it looks like when b equals 2, this limit exists. And it looks like the limit is about 0.6932 if you keep going. Let's do the same thing for b equals 3. We'll make a table for h's and the value of the thing inside this limit. So our table is going to help us estimate a limit when b equals 3. And the numbers we get are, so if h is 1, 0.1, 0.01. So then I get 2, 1.16, 1.10, and then we get 2/3, 1.04, and 1.09. So it looks like as my h's are getting closer and closer to 0, my l's are getting closer to the same thing. So in this case down here, it looks like L is getting closer and closer to 1.0986. So it's a different number. So a different base gives me a different limit. And just so we're clear, these numbers that I'm coming up with here, those are numbers that would go here. Those would be our multiplier. Okay. So if I was calculating the derivative of 2 to the x, I would get 0.6932 times 2 to the x. If I was calculating the derivative of 3 to the x, I'd get 1.0986 times 3 to the x. That's what I'm trying to do here. But let me take this a step further. So I'm going to do this for a bunch of different numbers. I'm going to say, make another table. So for different values of b, what is this coefficient? What is this multiplier? So I just showed that if b was 2, my multiplier was about 0.6932. If b was 3, my multiplier was about 1.0986. If I do all that process again for 4, I get a limit of 1.38. If I do it for 5, I get a limit of 1.61. And now let me just make b a little bit smaller. If I do a 1, I get a limit of 0. If I do 0.5, so let me move some of this around. So if I put in 0.5, I get a limit of negative 0.69. And then if I try 0.1, I get a limit of negative 2.3. So if I plot these numbers, so I'm going to plot at 2, I get just a little over a half. At 3, I get a little bit over 1. At 4, I get a little bit over 1.5. At 5, I get a little bit over that. At 1, I'm at 0. At a half, I'm a little bit below negative a half. And at 0.1, I'm down here. So look at these dots. They follow a pattern. They're trying to show me something. So take a second. Think of all the elementary functions that you know. And ask yourself, does this follow the pattern of any elementary function that we have a record of?
Logarithmic.
Was that Alexia? Yeah. Alexia sees logarithmic. What do other people think? I mean, so while people are thinking about it, if I've got, logarithms certainly do look like that. It certainly has that pattern. Anything else have that pattern? Could this be a polynomial?
The square root functions.
The square root function? Well, the square root function never gives you back negative numbers.
Oh yeah, because it starts at 0.
It starts at 0, yeah. So it's not going to be a square root. And in fact, if you make these b values smaller, these negative numbers get they get bigger and bigger in the negative direction. So it's not going to be a square root. It's not even going to be a shifted down square root. So it could be a polynomial. The answer, what's that? A rational, right? Because this looks like it might be a vertical asymptote, right? But let's look at something. Oh, what? Did I? Oh, wow, I skipped the whole page. Here, we're talking about functions of the form b to the x. And so what did I say about b? Way at the beginning, right here, b can only be positive. So this whole process only works if b is positive. And so when we look at this thing, you ask for, as a rational function, could I have negative b's? Well, I can't have negative b's in my process. So that kind of doesn't go with rational functions. They're only undefined at like isolated points. So it might not be a rational, but it could be, because rationals have vertical asymptotes. That could be on our list. But it can't be a polynomial, right? Because a polynomial, they always either go to infinity positive infinity on both sides, or one side they go to positive infinity, the other side they go to negative infinity. This here doesn't look like it's going to infinity. It looks like it's like leveling out. It looks like it's got a horizontal asymptote. So it's going to turn out that Alexia is right. That this is following a logarithmic pattern. Yeah, it's following a logarithmic pattern. And if we worked, trying to decide. What to say next. Oh, well, let's come back to that, okay? Let's come back and fill that in. Let's go back to this idea that the derivative of b to the x is equal to b to the x times the limit as h goes to 0 of b to the h minus 1 over h. Right, and we just spent some time looking at these limits on this table here, right? Because this is a table of those limits. And this function looks like it could be nice and continuous. So there's a place right in here between 2 and 3, right in here somewhere, where we cross the line y equals 1. So somewhere between 2 and 3, this multiplier is 1. So the question is, for what b is this limit equal to 1? Okay, i.e., for what limit is b to the x equal to b to the x? Because that would be pretty cool if we have a base that has that limit. Okay. So let's look at that for a second. So suppose 1 does equal the limit as h goes to 0 of b to the h minus 1 over h. So this means for h small, b to the h minus 1 over h is approximately equal to 1. So if we multiply both sides by h, we get this. And so let's add 1 to both sides. I get that. Now let's solve for b by taking the h, how do you say that? Take both sides to the 1 over h power. Okay. So what this tells me is that if this is true, then b is going to be equal to the limit as h goes to 0 of 1 plus h to the 1 over h. And if you make a table of values or whatever you want to do, you'll see that this is about equal to 2.71693 repeating. Does anybody recognize that number? This is the number we call E.
It's E.
Yeah, it's E. So this limit here equals E. So this tells us that the derivative of e to the x equals e to the x. And so we were messing around with this idea that we knew the derivative of b to the x was some function of b times b to the x. And if Alexia is right, that this is actually a logarithm, that would tell us that the derivative of b to the x equals log of b times b to the x. And our recent observation is that when b is the natural number e, then that log of b should be 1. So this log is the natural log. So it turns out it is indeed a fact. We've been collecting evidence. It's actually true that the derivative of b to the x is the natural log of b times b to the x. That's a formula for the derivative of an exponential function. Okay. And it follows that the derivative of e to the x then is e to the x. So now we know how to differentiate all the trig functions and all exponential functions. Okay. So we also know how to differentiate all the rational functions. And because we have the chain rule, we can differentiate all algebraic functions. And we can calculate derivatives of all those functions I just mentioned. What other functions do we are left for us to calculate derivatives of? Are there any other families? Did we get them all? Polynomial, rational, algebraic, and algebraic includes the root functions, right? Algebraics are like rational, or algebraics are like polynomials, but with possibly rational and negative coefficient or exponents. Exponential functions, trigonometric functions. What else? Any other families of functions we're missing? We got them all? Narrator? No, they don't. What do we miss? Polynomial, rational, algebraic, inverses. Okay, that's not a family of functions, but yes, we don't know how to differentiate inverses yet. That's good, Robert.
Piecewise.
Piecewise, we can always, piecewise are built out of other elementary functions.
Oh,
And so-
absolute functions.
Absolute functions? What do you mean?
Oh no, I was just saying, I don't, are they one and the same? Because absolute is part of piecewise, right?
Yep, absolute is a kind of a piecewise function. Yeah. Anybody else want to guess what the last one is? You want a hint? It's an inverse. It's an example of an inverse function. It's the inverse of an exponential. What do we call them? Anybody? Begins with an L. Anybody?
Logarithmic.
Yeah, right. Right. It's actually one written right over here, right? And another one right here. So in a little while, we'll figure out how to differentiate inverses and differentiate logarithms. We'll wait a couple of days on that. Now that we've got exponentials and trig functions, that's enough for right now. So you want to take a moment and do some chain rule with exponentials and trig functions?
Sure.
Sure. All right. So let's differentiate sine of 2 to the x. So I'll do this for you. I'll walk you through the way I think about it. So here's my inside function. It's the first thing that happens to x. X goes to 2 to the x. So I'm going to call that f of x. And then what happens is the y takes that output and does something to it. So I'm going to call the sine function my g. And so written this way, A is g of f of x. That's g of 2 to the x, because f takes x to 2 to the x, and then g takes its input to the sine of the input. Okay, so that checks out. So this is a way of me checking. You should always check. So next I'm going to take the derivative. So the derivative of a to the x, I'm going to use the chain rule. It's g prime times f prime. Well, what's g prime? So going and looking at g prime, that's the derivative of a sine. Well, we said that's a cosine. And what's f prime? F prime, that's the derivative of 2 to the x. Well, that's 2 to the x times the natural log of 2. So a prime is g prime, which is cosine of y, times f prime, which is 2 to the x log 2. And I'm sorry, I'm so low on the page. This is cosine of 2 to the x times 2 to the x times log 2. Right? That's the derivative using the chain rule. It looks pretty gross. It's pretty long and involved. But it's really just the result of 2 derivative formulas we have. I've got 2 more minutes. Let me see if I can do 2 more examples. What about 2 to the x squared plus 3x plus 1? So here I'm going to say my first function is this polynomial because x is taken to the value of that polynomial. And my second function is the function that takes the value of that polynomial to 2 to that value. And so I think b of x is g of f of x. And let's just double check that. G of polynomial. And then g takes the input and puts it in the exponent of 2. All right, so that checks out. So then the chain rule tells me b prime is g prime times f prime. Well, what's g prime? Well, g prime, that's the derivative of 2 to the y. So we know that's 2 to the y times the natural log of 2. And f prime, well, that's easy. That's just a derivative of a polynomial. That's 2x plus 3 in this case. So just moving things around a little bit, that's 2x plus 3 times the log of 2 times 2 to the y, which I'm going to write as 2 to the x plus 3x, or 2 to the x squared plus 3x plus 1. Right? So that's that derivative. And I'm right at 9:50, so if you got a jet, no pun intended, jet. So what about sine squared x? Well, here, the first thing that happens to my input is the sine function. It goes to the sine function. And then that value gets squared. So this is how I'm going to write c of x as a composition. So c of x, I think, is g of f of x. So that's g of sine of x. And then sine of x squared. So that checks out. And right, this is special notation with trig functions for that. So this tells me c prime is g prime times f prime. G prime is 2y, right? Because g is that's just a polynomial. And f prime is the derivative of sine, which is cosine. So, and y in this case is sine. So there we go. The derivative of sine squared x is 2 sine x cosine x. Another way, I like to think of this is the way I learned it when I was learning this stuff for the first time, is in my mind, I would rewrite this like this, and then I could see the power rule. So when I was differentiating this, I take the 2, make it into a coefficient, leave the sign alone, reduce the exponent, and then apply the chain rule and put the derivative of the sign. Okay. So this is a nice, careful way to do the calculation. But once you get comfortable with this notation for powers of trig functions, you start seeing them in this way, and then you can kind of use them like you use the chain rule like you do for monomials. All right, so that's where I'll stop. I'm over time. Thanks for hanging with me if you could. No time for questions really. Lecture videos are up to date, I believe. Lecture notes are up to date. Make sure you watch those and the other screencasts. And I'll see you in office hours if you want to talk, but keep doing those learning target quizzes. Keep taking them. All right, I'll talk to you soon.
All right, thank you.
Stay well, stay healthy.
No, stop.
Will we have a meeting
No,
this week?
no.
Is that you? Is that you at your house, Lupe?
Yeah, that is. I'm
Yeah,
sorry,
okay.
my dog's acting up right now.
Yeah, no, that's fine. That's fine.
Yeah.
Yeah, let's talk Thursday.
Thursday?
Yep. Okay.
Okay then.
I'll see you then at 3. All right.
Okay, bye.
Good luck with your dog.
Thank you.